So that will be useful. So let's look at how instruction encoding is done. So we were looking at the SimpleRISC ISA, which is a 32-bit ISA. And in this ISA, let's say we have 21 instructions. Now, for encoding this 21 instruction, you need at least 5 bits, because if you only reserve 4 bits, so what we are trying to do, we have our instruction is 32-bit. Now we have to allocate this 32 bits for different tasks. For example, there will be some part of this 32-bit will be denoting that my opcode, so that while I design the hardware, so remember that we will talk about how this instruction will be decoded, because my hardware will get this bit 32 bits, and by reading those 32 bits, it has to figure out what needs to be done. So some part of it will be denoting the opcode, and rest of it will denote maybe operands and few other things. So now, how many bits I should reserve for opcode? That will depend on what are the different kind of things I want to do. What are the different instructions I have? So we are saying that in SimpleRISC, we have 21 instructions. So what are these 21 instructions? So we have all these instructions listed out. Some of them are arithmetic, some of them are basically logical. Then you have again logical, then shift instructions. Then you have this, okay, this is an interesting instruction which will come to later on. So no op is basically do nothing. We need this when we implement pipeline, etc. We'll talk about it later. Load, store. Then we have the branch instructions. So branch can be branch if equal, branch if greater than, unconditional branch. Then you have this call and return, this kind of instruction. So we have this 21 instructions. Now, how many bits we need to represent this 21 instructions without uniquely? So for that, we need at least 5 bits, because 2 to the power 5 is 32. So we can't use 4 bits, because with 4 bits we can only have 16 instructions, but we have 21, so we need to use 5 bits. All right, so that part I guess is absolutely clear to everyone. Now, okay, please feel free as always, if you have any questions, feel free to stop me. Now then, if we look at our basic instruction format, so we have this 5 bits reserved for the opcode. We are left with 27 bits, and with this we have to basically specify other things which are required in the instruction. So now if we remember how our instructions are formatted, add, actually we can have a destination register where the result or outcome of this addition operation will be stored. Then there is a source register 1, and then there is a source register 2. Now in this kind of arithmetic operation, the second source can be a register or can be an immediate value. All right. So now with these 27 bits, I have to represent my destination, both the sources. Now one of the source can be an immediate as well. So this is true for add, subtract, multiply, division instructions. All right. If I come to this even mod and all these operations, if I come to compare, I see that now my number of operand has been reduced. So instead of 3 explicitly mentioned operand, since I am comparing between 2 numbers, I have only two operands to deal with. So I have a source 1 and source 2. So comparison instruction compares them and accordingly takes a basically sets or resets some flags. The flags dot equal, flex dot greater than, etc. Then you have these logical instructions where you have again two operands. Basically in logical AND you have three operands. So basically one where you will be storing your result, the destination, and then there are two sources, and those sources one of the sources can be immediate also. So you can look at them and you can see. From load,
Sir,
yeah.
sir,
Yeah.
sir, in the not operation, can't we do like that not of RS2? Means we can use only one of them, which is complementing the value of register 2.
So you can do that. Now, let's say I want to do that. Okay. But how, where your result will be stored? If you say that I will store the result in the same register, which is the source, then many a times it might lead a problem. Let's say you want to do this kind of a thing. Let's say A equals A bar. Whenever there is a NOT operation, you store the inverted value here itself in this variable. Then you do not have A bar available to you. So if you need to use both A bar and A, then you have to do this back and forth. So rather than that, you are saying that, okay, I'll store a new destination, or I'll just assign it to a new variable. Let's say I'll store the value of A bar in C, and that's where your destination and source comes in.
But sir, if we like only one register, then the source is also that register and destination is also that, right?
In SimpleRISC, you don't have that thing. In SimpleRISC, it's not a basically you have to explicitly mention what is your destination and what are your sources. That
so
depends.
we can do like that, not RS2, RS2.
You can do that, but there you are mentioning that your RS2 is only your destination. So you are not skipping mentioning the destination. So you remember the machine model. So here you are explicitly mentioning what are the operands. You might be using the same operand, but you are mentioning it.
Sir, we have to mention both source and destination.
Yes, yes. It's not implicit. For example, if it was an accumulator based system or let's say stack based system, then it would have been implicit. You don't have to mention where the inverted let's say RS will be stored. Okay. All right. So also this kind of uniformity that, okay, you might ask that, okay, why every instruction we are explicitly mentioning a destination and then source? This kind of uniformity makes your decoding much simpler, because you have to remember that ultimately this instruction format which I am building, it has to be decoded by a hardware, and then the hardware will hardware needs to be implemented. So if I make it very complicated, let's say for one instruction I define the first operand as source, another instruction I define the first operand as destination, then all sorts of complications will be there, because then you have to now specify that, okay, this field can be a source operand or it can be a destination operand. Now you have to have some other field specifying that whether it's a source operand or a destination operand. So that increases complexity. So we don't want to basically we want to make things as simpler as possible. That's why we would like to have as uniform structure as possible. So for all the instructions, this is fine that you can define a destination and a source, because for example, move, you can say that, okay, this is my destination of the move operation and this is where I have to move. You look at any other instruction, whether it's let's say shift operations, or for load also it's fine. For load, I know that this is my basically destination where I have to store the, or basically get the data from memory and load it here. But this becomes little tricky for a store instruction. Now, in store instruction, basically this is the memory location where I want to store the data. And which data I'll be storing? I'll be storing the data which is there in this register. Now see, this is an exception where in this instruction format, we have always said that the first operand is your destination operand. But in case of store, it's little tricky. Your destination here is this immediate this memory location. So that's where you want to store the data. Now you might say that, oh, I don't want to violate this protocol which I have set out with, that destination comes first, then the source. Now, if you want to honor that, you think that now you have to significantly change your instruction format to accommodate one instruction, which is the store. Now there comes the trade-off. Now as a architect, you have to now take a call. Is it worth making all these changes for one instruction, or for this store, I'll just assume that this destination is actually my source? Because in this store instruction, there are two registers involved. One is the offset and one is this register from where I have to store the data. So these are both are basically source registers, and this whole address is my destination. So what is a better trade-off here is that just assume that, okay, store is an exceptional instruction where, though we say that, okay, this is a basically this register whose data need to be stored, we put that register as the first operand, and we basically store the value in the memory location. So here, though the name says that it's a destination register, actually it is not the destination register, and this is an exception. We might even spend some more time in the stored instruction later on if required. So this is the only instruction in our SimpleRISC where we are not following this protocol that the first operand is always your destination operand. Okay, and then yeah.
So it is not good that we will change the whole format of the instruction only because of this command. Because if we do that, then all other command will have different syntax.
Absolutely, and the kind of overhead you will have does not make sense, right? Because it's not only going to affect your this one instruction, it will have an impact on all the other instructions. So it doesn't make.
If we do the change, then this instruction will be correct, but all others are incorrect.
Basically, then you have to have an identifier that whether it's a stored instruction first. You have to, whenever you want to decode it, you have to first look at, okay, if it is a stored, then this basically instruction format need to be considered differently than for other instructions. So which does not make sense. All right. So we will, while we talk about decoding instruction or the hardware, we will face many such choices, and then you will basically it will become very intuitive that, oh, basically the kind of gain I will get and the kind of price I have to pay for achieving that, maybe they will be completely disproportionate. So then the choice becomes very, very simple.
Sir, in the syntax of the load instruction, there is a comma between the RD and
so basically this is comma, just like all the other instructions.
Sir, it seems to be a dot, so yes.
Yeah. So yeah, this was a printing mistake. Yeah. Okay. Another interesting thing to observe, which I have not highlighted, if you look at it, the branch instruction always starts with 1. So you can basically exploit this, because if you can, we will talk about when we look at a pipeline, then if you can decode whether it's a branch instruction early enough, then I think I mentioned to you earlier that, or maybe I have not mentioned to you guys, that there are some hazards of pipeline. So whenever there is a branch instruction, so whatever you have speculatively fetched in your pipeline, that basically need to be discarded. Now, if you can decode whether there is a branch instruction next or not very quickly, then it helps you to figure out where to get the next instruction from. So now, since this all the branch instruction starts with 1, so maybe you can have in the decoder, you can just have a check that whether the first bit of the opcode is 1 or not. If it is 1, then you know that it's a branch instruction, and you alert all the other things in the system that a branch instruction is coming. So don't speculatively fetch, or even if you have fetched, just stop now till we figure out whether the branch has to be taken or not taken, and so on. So just an observation. We will talk about it in more detail going forward. All right. Now, so we have this 32 bits. Now, what are the options we have? So we said that the opcode will take 5 bits because we have 21 instructions to accommodate. Now, if it is, if your instruction only deals with registers, now in SimpleRISC we have 16 registers. So to uniquely identify each of the register, I need 4 bits. So this is my destination register. This is my source 1 register, and the source 2 can be a register or can be an immediate value, right? Now there are 2 options. Any instruction, so all these instructions we have looked at, the second source can be an immediate or a register. Now I should have some information, or some in the encoding itself, I should somehow indicate whether this instruction has immediate as a source or a register as a source. All right. So how do I do that? I have a specific bit reserved to indicate that. I have a single bit which tells if it is 1, then I know that the second source is an immediate. If it is 0, then I know that the second source is a register. All right. So this is our SimpleRISC encoding. So we are saying that opcode, it's basically 5 bits to denote what kind of instruction it is. This I bit, if it is 0, that means the second operand is a register. If it is 1, then the second operand is a immediate value. Then the destination register is denoted as RD. I need 4 bits for that. Source register 1, which also needs 4 bits. And if it is in this example, we have all 3 registers. So I will have source 2 also as a register, and I need 4 bits. So you see that if I have an instruction where I am only dealing with registers, I don't have any immediate value, then actually I'm not using all the 32 bits. I'm using 10 plus 8, 18 bits. So with 18 bits, I'll be able to, basically 18 bits are enough to tell me what that instruction needs to do. I have already specified what operation, what are the, where the results should go, and what are the sources which should be used. All right. So this is the register format, and I will be able to know that I am dealing with only register by looking at this bit, immediate, the 6th bit here. Okay, so it depends on where from you are counting. So basically these 5 bits and the bit which is following that will tell you whether you are dealing with only register or there is an immediate value. I hope this is clear. If you have any questions, please feel free to ask.
what about the other bits?
Those other bits will be unused when you are only dealing with this kind of an instruction where you are dealing with only registers.
You do not need to add any zero or anything.
No, because you can feel free to add, but the decoder, because where this instruction will go, this instruction will go to a decoder. The decoder will decode that, okay, this is the operation I need to do, AND operation. This is the source. These are the two sources, and this is the destination. I do not need any other information, so I'll just not treat these informations. Right?
But sir, it is a RISC ISS, so it cannot handle instruction of variable length.
The instruction is not of variable length. So you can very well, basically all instructions are of 32-bit. It depends on how many bits you are using. For example, if I have a no-op operation, do you call it a variable length? So no-op, only opcode will be there. Nothing else is required, right? So I have dedicated fields for each of these, my source, destination, and all these things. I'll not be able to make one instruction longer than this, another instruction just with 5 bits. So you can come back and say that, oh, for no-op, I need only 5 bits. So why I should reserve 32 bits? So in RISC, it says that come what may, you have to use 32 bits. Maybe you will not be using those bits. If you allow variable length instruction, then your one instruction can be of 5-bit long, another instruction can be of 32-bit long, another instruction can be of 80-bit long, and so on. So you are not allowing variable length, but you might, for some instruction, you might have unused bits. So all instructions are of 32-bit, but for some instruction, some bits will not be used. That's the penalty you pay for fixed length instructions.
But for, sir, in this example, we can take only 18 bits because we require only 18 bits, right, for all instructions.
You can, but as I said, like your decoder will become increasingly complex. You want to make your hardware simple. Now today you have this instruction, so you will have 18 bits. Now you will have a different mechanism to read these 18 bits. Now again, another instruction comes which has an immediate operand. Now that will require 32 bits. So then what you will do? So try to visualize what the hardware will look like. So this 32 bits will go to a decoder. The decoder will decode it. It will appropriately initialize your ALU. It will provide the basically the operands to the ALU, and the result, where the result has to be stored, that will be also specified after by looking at the instruction. So if you have a fixed basically field for each of these values, then it is much more easier. For example, you get this 32 bits, you look, okay, this is the opcode. So accordingly, the ALU can be initialized that, okay, you need to do the add operation. You look at this bit, oh, there is no immediate value. So you get all your operands from this like next this fields. So register destination register from this 4 bits, source 1 from this 4 bits, and source 2 from this 4 bits. If it is 1, then you know that, okay, I'll get my destination source 1, and rest we will talk about how the immediate looks like coming. So basically, to make your hardware simpler, you have to follow some standard process, and that's what we are doing. You can do all these variable lengths. There are advantages of variable length, but there are also a lot of overheads because of this variable length. So we should be aware of that. That's why there are SimpleRISC processor where you do have variable length instructions. Now let's look at immediate format, because that's what we wanted to discuss, and that's why we came to this or we take this detour. So now let's say I have an instruction where I have immediate values. So I know from my previous discussion that I need 5 bits for opcode, 1 bit for saying whether there is an immediate one of the sources is immediate or not. Then basically destination is a register, source 1 is a register. Now you see that how many bits you have utilized till now. You have used 14 bits here, 5 for opcode, 1 for this denoting that whether immediate source is used or not, 4 bit for destination, 4 bit for source 1. So you have used basically 14 bits. Now out of 32 you have used 14, so you are left with 18 more bits. Now I have 18 bits for my immediate value. Now we also discussed about modifiers. So modifiers, we said that modifiers can be of 3 types. It can be default, U modifier to indicate that the immediate value is unsigned, and the H modifier to indicate that the basically immediate value should occupy the higher bytes in the register or in the destination. So now I have these 3 modifiers. Now to basically identify these 3 modifiers, I need 2 dedicated 2 bits at least, because 1 bit will not be sufficient to identify the 3 modifiers. So that's why I use these 2 bits to denote the modifier. So whether the modifier is U, H, or there is no modifier, basically by default modifier, that is indicated by this 2 bits. Now, how many bits we are left with for immediate? We are left with 16 bits for the immediate. So that's where the 16-bit limitation comes for our immediate value. All right. Because and in this case, you see this, in this instruction, we have used all the 32 bits. There is no unused bit. All right. So I think this makes sense, right? Please feel free to ask if you have any questions.
Sir, the immediate is of 16 bits and our destination register is of 4 bits. So how can you store the value? How can it accommodate those 16 bits? It can only accommodate 4 bits.
We can accommodate?
Sir, the destination register can only accommodate 4 bits, right?
This is the destination register identifier. I have 16 different registers. To identify each register uniquely, I need 4 bits because 2 to the power 14. So my register 1 can be denoted as 0000, 4 bits. Similarly, register 15 or register 16 can be denoted as 1111. So I need only 4 bits to identify uniquely all the 16 registers. But each register is 32 bit. I'm not talking about the content of register. I'm talking about the address of register. All right.
Yes, sir, it's clear. I got confused.
Oh, okay. Yeah. Any other question?
Like, sir, like we are converting immediate like 16-bit to 32-bit. Similarly, like you mentioned, like the reference to since there are total 16 registers, so we can represent the different, like we can divide them using 4 bits. So basically, we can have 16 different registers. So like when we are having an opcode of 5 bits, so that is also converted into 32-bit while processing.
No. So I have 21 instructions, if you remember. So now I have to uniquely identify this 21 instruction. So for example, in the opcode, if it is written that 5 zeros, the decoder has to decode that, okay, this corresponds to add. So I have 21 different instructions. I have to uniquely identify each of these instructions. So I am just assigning some unique identifier to each of these instructions. And to do that, I need 5 bits because basically 2 to the power 5 is, I'll be able to have 32 different unique numbers, and I can basically accommodate 32 instructions. But I have only 21 instructions, so I will have few codes which will be unused. Why I need?
So like my doubt is like like you said, like the register would be of 32 bits only, right? The actual value in the register would be of 32 bits only. So since our processor is 32 bits, so like I am asking, like everything which is processed is is converted into a 32 bit like 32 bit number.
Yes. So if you are talking from this immediate point of view, so
Yes,
let's say this can be a move instruction, right? So this opcode can be moved, and the destination register can be, let's say, R2, and source can be, let's say, an immediate value. So in the immediate value, I can only specify 16 bits, right? But this R2 is 32-bit register. So I have to somehow convert this 16-bit into 32-bit. Now, when the processor tries to convert, the processor is given some hints that how should you convert, and that hint is given in this modifier bits. So if it is by default, then it will just extend the sign bits and it will convert those 16 bits into 32-bit. If it is unsigned, then it will basically put zeros on the front of this 16 bits to convert it into 32. And if the modifier is H, then it will put this 16 bits as the more significant bytes, and the lower significant bytes will be basically populated with zeros. Does this make sense?
No, sir, like my question is, like since our processor, like since our ISA is 32-bit, right?
Yes.
Which supports 32-bit instruction.
Mm-hmm.
So like everything we are converting is into 32-bit. Like we have an immediate of 16-bit. Like we can, like we just saw, like we can have a maximum of 16-bit immediate, and we finally converted to 32-bit.
Because, as you rightly said, my processor is 32-bit. That means the ALU is also 32-bit. Any arithmetic operation you want to do, the ALU by default will assume that your operands are 32-bit. Yeah.
Okay, so we only need to convert all the operands or the register, the value stored in the register to be of 32-bit. Rest can be like my doubt was like opcode is of 5 bits. So we don't need to convert that into 16-bit to like the processor don't need that to be 16-bit to be read.
No, because opcode, you are not actually using this value to do some arithmetic operation. Opcode is an indicator that what instruction you should do or what kind of task you should do. So opcode is there to uniquely identify the current task I need to do. So if I give an instruction add, because the machine will not be able to read add, so I have to give ones and zeros. So the add is converted into a stream of 5 bits, which the machine will decode as an add operation. The arithmetic operations are getting done with these operands. So the operands has to be 32 bits.
Yes, sir, got it.
Okay.
Thank you.
Excuse me, sir.
Yeah.
Sir, why the store operation is different from other operations? Can you explain, sir? I didn't get that, sir.
So basically, you see that in this instruction format, there is a destination register and then there is a source register. So this is typically all the format of all the instructions. Now, what happens in a store instruction? In a store instruction, let me see whether I have this. Actually, we are running out of time. Let me, if you guys are fine, I can go on. I was just thinking like whether I can address this store part also here. Okay, so I'll just go back and explain it from this. So for all instructions, you see that we are specifying that this is your destination. So destination can be destination for, let's say, the load. So when we say the destination of load, that means I have this destination register where I want to bring some data in from memory and store, put it there. So this is my load operation. Now what is happening in store? In store, let's say I have some value in register R2 and I want to store it in a memory. All right, so this is my memory. So if you look at the store instruction, then we always say that the among the operands, destination should come first. Now, what is the destination here? Destination is this memory location. So ideally, if we follow the same protocol, then we should have written an instruction like this, where store, then destination, and the source, right? Now, what is this destination? Destination is the memory, and memory we will be we can denote it by immediate values, because we have seen that this offset, the addressing mode, where there is a offset and then there is a register which basically shows the base of that memory address. Now, if I have this format, then in the instruction, I will have something like this, that store, then this immediate, then RS, the source, and then the other source where from the value need to be taken. Now, if I look at all the other instructions, I never had an instruction where the first operand is an immediate. All right. So this is the uniqueness of the store instruction, where the destination is an immediate value, and we have taken. So these are some protocol decisions we have taken. We said that okay, destination is the first operand we will write always. Now here is a contradictor, and we also said that the immediate values should come as the second operand. Now here we have a contradiction. Here the destination is an immediate value, and if we want to follow either of this protocol strictly, that immediate value should come at the second operand or destination should come as the first operand, then there is a issue. So we have to take it. So why this is an issue? Then your decoding becomes very difficult, because we have said that this first operand is always a 4-bit, can be reached by a 4-bit, because this is a register. The second operand can be also basically identified by this 4-bit, because this is also a register. But now for if stored, if you want to put an immediate value here, so it will require 16 bits here. So now if I read the opcode, so think about how the decoding will be done. So at the decoder level, you read the opcode, you realize that it's some other instruction other than store, then you know that is okay, this 4-bit is register, this 4-bit is register, and so on. But as soon as you realize this is a store, then you have to completely change this. You have to say that, oh, the first 16 bits or whatever, like whatever number of bits you reserve for immediate value, now these values are your immediate value. So you see that hardware wise, you have to have enough mechanism to select depending on whether it's a stored instruction or any other instruction. So instead of making things so complicated, another way could be you just take this stored instruction as an exception, and you say that okay, though we said that destination has to come first in the instruction format, we will ignore that and we will say that okay, the source register itself will be denoted first in the store instruction, and we will ignore that this is the source and this is the destination. Basically, in the store instruction, the source and destination has been swapped. So that is the uniqueness of this store instruction. Okay, sir. Hope this makes sense.
Yes, sir. Got it, sir.
So the assembler will take care of it as you encounter the store command, right?
Can you repeat?
So the assembler will take care of it when it encounter the store command, that what is the destination, what is the source.
Yeah. So the whenever the stored instruction goes, so basically the decoder knows that okay, the first register is the source from where I have to store the value. So it's just how you basically interpret, because the decoder will know that okay, this is the location from where I have to get the data, and this is the location, memory location, where I have to put the data in. Yeah, so at the decoder level, you will be able to do that. Okay, so I think we have already crossed our time, so I'll stop here, and I'll be happy to